Hello, welcome to this talk titled Statistical Guarantees for the Stationary Points of Shallow and Linear Neural Networks. This is Mahsa Taheri, PhD student in the Department of Mathematics from University Bochum, and this is a joint work by Fangzi and Professor Johannes Lederer. What I would like to talk about, it is non-convexity issues in deep learning. As you know, the optimization of non-convex objectives is challenging in a sense that optimization algorithms just guarantee convergence to a stationary point and not a global optimum. Although statistical guarantees for global optima are abundant in the literature, like our previous study, such guarantees for the practical counterparts are rare. Recently, Elsner derived some oracle inequalities for the stationary points. They basically considered a general non-convex objective function made by a non-convex loss plus a convex penalty. But the point is that the result need to verify 2-point marginal condition on the theoretical loss, which is kinda restricted a strong convexity condition in the literature. But the point is that verifying such condition is not easy, especially for neural networks. What we would like to do in this work is extracting sharp oracle inequalities for stationary points of regularized linear neural networks with one hidden layer called basically shallow linear neural networks. And we actually do some assumptions verifying such result. Let us start by giving a formulation of the problem. As always, we consider that we have n data examples. Xi's are feature vectors from dimension D and yi's are corresponding real outputs. We assume that yi's are generated by implying an unknown function f on xi plus some noise. And the motivation of this work is approximating the unknown function f using linear and shallow neural networks, which denoted in this work by a vector gamma and a matrix theta. Our estimators here, gamma hat and theta hat, which are the minimizers of an objective function made by a least square term plus a penalty, which we are basically penalizing over the L1 norm of weights. We use the notation of vector to generate a vector from a vector and a matrix, and we are actually summing up over the absolute value of all the weights in the network, and R here is our tuning parameter. Our parameter under consideration here is beta, which contains all the pairs gamma and theta, which the subnorm of theta and L1 norm of gamma are bounded by second root of log of n. Due to the non-convexity structure of neural networks, objective functioning too is non-convex, and so convergence to a global optima is not guaranteed by optimization algorithms. We use two measures of accuracy. The first one is in-sample prediction error, and the second one is generalization error. And we also define beta tilde as a stationary point, which is basically a vectorized version of pair gamma tilde and theta tilde as a stationary pair if they satisfy this inequality, which is basically first order necessary condition for a pair gamma tilde and theta tilde to be an optima of the problem. For simplicity, we do some assumptions that xi's are IID random vectors between 0, xi's, entries of xi's are independent, and the subnorm of xi is bounded by a positive constant m index x. We assume UI are centered Gaussian random variables and they are independent of xi, and we assume that theta transpose have full rank. But thanks to our proof approach, we think that we can easily relax this result in further study, these assumptions in further studies. And here is the main result of this work, which we extract statistical guarantees for all the stationary points. We prove that once the tuning parameter is selected large enough, then any stationary point, gamma tilde and theta tilde of the objective function into verify such oracle inequality, which basically our theory proves that for properly chosen tuning parameters R, any stationary point generalizes essentially as well as the best possible network in the class under consideration. Here we actually have the best approximation, and here we have excess error. And here we define the optimal tuning parameter as R oracle, which there are some important factors here. The first is upper bound of subnorm of xi's, and rates are divided by second root of n. To prove this theorem, we use two important technical results, which are main ingredients of the proof approach. The first one is studying the behavior of Hessian matrix. And in this proposition, we prove that the Hessian matrix of generalization error in a scaled version of parameters is positive semi-definite. Alpha here is a vector from dimension W, which is the width of the network, and its elements are 1 divided by C, which C here is called the scaling factor. And basically this idea comes by the well-known the fact in neural networks that weights can be rescaled across the layers in neural network. And it says that once we multiply the elements of one layer of the neural network by a positive constant, and if we divide all the elements in the next layer by the same value, then the output of the neural network doesn't change, but of course the behavior of Hessian matrix will change. And we prove that once this scaling parameter is large enough, then we can prove that the Hessian of generalization error is positive semi-definite. Maybe let me to introduce our notation of gamma star and theta star, which are actually the parameters of the best approximation of the target function f in our parameter space. Another technical result, which is one of the main ingredients of our proof in Theorem 1, is employing the tools of empirical process. And this lemma basically says that how we can choose the best tuning parameter. And we are actually upper bounding the absolute difference between gradient vector of in sample prediction error minus gradient of generalization error in a neighborhood of the best approximation of the target. And this lemma helps us to choose our oracle. And let me quickly go through the proof approach in our Theorem 1. We basically start by writing second order Taylor expansion of generalization error in a scaled version of the gamma star and theta star. We continue using a definition of stationary points, and we continue by our result in lemma 3 to choose the suitable tuning parameter. And finally, we use our result in proposition 2, which is positive semi-definiteness of the Hessian to improve our bond. And finally, I would like to finish the talk by a quick discussion about importance of linear neural networks, which are basically theoretical understanding of them is of much interest, especially in recent years. And maybe one motivation is that previous empirical studies shows that optimization theory of linear neural networks may exhibit some properties of nonlinear models, which are difficult to analyze. And thanks to our proof approach, we hope that we can extend our result to deeper networks in further study. Let me to finish the talk here, and thank you very much for your attention.